Hello, in this lecture we'll answer on two questions. In the first question, we find out the radius of this small circle, and in the second question, we'll find out the area of this green shape in two different methods. We start with the first question. In the drawing we have a quarter circle. A or B is a quarter circle. We know that 9/7 OB equals to 60 units in its length. Inside this quarter circle we have a semicircle and this small circle, and our mission is to find out the radius of this small circle, or to find out the value of R. Okay, so first of all, we know that AOB is a quarter circle, therefore this angle AOB equals to 90 degrees in its size. In addition, because of the fact that AOB is a quarter circle, it means that sides AO and OB, they are both the radii of the quarter circle, and therefore they are equal to each other. But the radius OB of the quarter circle equals to 16 units in its length, therefore the radius AO must be also equal to 16. So AO equals to 16. And the radius of the quarter circle, AO, the radius of the quarter circle, it is also the diameter of this semicircle. So we know that the diameter of the semicircle equals to 16 units in its length. Therefore, the radius must be equal to half of it. The radius must be equal to 16 over 2, that is 8. So we define the center of this semicircle, this point is point P. Therefore the radius AP equals to 8 units in its length, and the radius PO of the semicircle also equals to 8 units in its length. In the next step, we define the relevant points to this question with letters. We define the center of this small circle as Q. This point is Q. We will define the point of tendency of tangent OB with this circle, this point as point M. We will define the touching point of this semicircle with this circle, with this small circle, this point as point S. And finally, we define the touching point of the big quarter circle with this small circle, this point is point T. Okay, so here, in the next step, we'll do a construction. That is to say, from point Q, we'll go perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. PO is the radius of the semicircle, that's equal to 8 units in its length. And here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have the radius QM of this small circle, that is the radius that we are looking for. The radius QM is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to the radius MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So here we have quadrilateral QMOH. Inside this quadrilateral QMOH we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral QHOM, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral HUMO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO. But QM equals to R, it is the radius of this small circle, that is the radius that we are looking for. So QM equals to R, therefore the opposite side HO must be also equal to R. So what is the length of line segment PH? On Laurent is very easy to see that PH equals to PO minus HO. Again, PH equals to PO minus HO. So I write it down. PH equals to PO minus HO. So PH equals to PO. PO is the radius of the semicircle, that is equal to 8 minus HO. We just write down further that HO equals to R. So in total, PH equals to 8 minus R. PH equals to 8 minus R. So in the drawing, we have an external notch between the semicircle and this small circle. That is to say, they are touching each other externally at point S. And therefore we can implement here rule 10. I'll repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. Okay, so here we have two circles. They touch each other externally at point P. The center of this circle is there at point O. The center of this circle is there at point M. And the straight line that connects their centers together is of course the straight line OM. The straight line OM, according to this rule 10, must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, this semicircle touches this small circle externally at point S. The center of this semicircle is there at point P. The center of this small circle is there at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point S, that is their touching point. Or PSQ is one straight line. Or P S Q is one straight line. So we connect points P and Q together by a straight line, and we know that the straight line PQ must pass from point S. We can see that the straight line PQ indeed passes from this point S. So if PSQ is one straight line, it means that PQ is a straight line. But what is the definition of line 7PS? Line 7PS starts from point P, that is the center of the semicircle, and ends at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units in its length. What is the definition of line cement QS? Line cement QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R. R is the radius that we are looking for in this question. So according to rule 10, PSQ is one straight line. Therefore, it means that PQ must be equal to PS plus SQ. So I write it down, PQ equals to PS plus SQ. So PQ equals to PS plus SQ. So PQ equals to PS. PS is 8, it is the radius of the semicircle, plus SQ. SQ is R, it is the radius of the small circle. So in total, PQ equals to 8 plus R. PQ equals to 8 plus R. So in the next step, I will copy the grain right triangle PHQ in a new page, and we implement the Pythagoras theorem on this right grain triangle, triangle PHQ. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. We already found out that the hypotenuse PQ of the green triangle equals to 8 plus R, and side PH equals to 8 minus R, and side HQ is the missing side. So actually, this is the right green triangle PHQ that I got it from the original drawing. According to the Pythagoras theorem, in this triangle PHQ, PQ square equals to PH square plus HQ square. Again, PQ square equals to PH square plus HQ square. So write it down. PQ square, that is the square of the hypotenuse, equals to PH square plus HQ square. Okay. The hypotenuse PQ equals to 8 plus R, therefore PQ square is 8 plus R square, and it is equals to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we write as it is. So 8 plus r squared equals to 8 minus r squared plus 8q squared. Here we'll open the brackets on both sides of this equation, on both sides of this equation, and we get that 8 plus r squared equals to 8 squared, that is 64, plus r squared, plus 2 times 8, that is 16, times r. So it is 16r, and it is equals to 8 minus r squared. 8 minus r squared equals to 8 squared, that is 64, plus r squared, minus 2 times 8 is minus 16, times r. So it is minus 16r plus hq squared. So here we have 64 on both sides of this equation, so 64 will get cancelled. We have also r squared on both sides of the equation, so r squared also will get cancelled. After cancel those two expressions, in this side of the equation we left only with 16r. In the other side of the equation we have minus 16r plus hq squared. Here we add 16r to this equation, and we get that 16r plus 16r is 32r. So 32r equals to hq squared. So here we substitute 32 by 16 times 2, and we get that this expression in total will be equal to 16 times 2r equals to hq squared. So here we take a root out of this equation, and finally we get that hq, the missing side hq, equals to the square root of 16 is 4. Inside the root we left only with 2r. So in conclusion we found out that the missing side hq equals to 4 times square root of 2r. This is the missing side HQ. This is the missing side HQ. And it is equals to 4 times square root of 2r. But we have already found out that for the other HQMO is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side MO. But HQ equals to 4 times square root of 2r, therefore MO must be also equal to 4 times square root of 2r. So in the drawing, the big quarter circle touches this small circle at point T. So the two circles touch each other at point T. Therefore, we have an internal notch between the big quarter circle and the small circle. Okay, again, that is to say they are touching each other internally at point T, and therefore we can implement rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. Here we have in the drawing two circles. The center of this big circle is here at point O. The center of this small circle is here at point M. And the two circles touch each other internally at point P. This point P. Therefore, according to this rule, Rule 9, the straight line that connects their centers together is of course the straight line OM. According to this rule 9, the straight line OM must pass for their touching point, that is point P, or OMP is one straight line. Again, OMP is one straight line according to this rule 9. So I can actually implement rule 9 in our drawing. the big quarter circle touch the small circle internally at point T, and therefore according to rule 9, we know that the straight line, the center of the big quarter circle is there at point O. The center of this small circle is there at point Q, and the straight line that connects the centers together is of course the straight line OQ. And according to rule 9, the straight line OQ must pass from point T, that is the attaching point. Or OQT is one straight line. Again, OQT is one straight line according to rule 9. So we connect points O and T together, O and Q together by straight line, and we know that the straight line OQ must pass from point T, that is the attaching point. The same from the knowing that the straight line OQ passes from point T. But what is exactly the definition of the... We know that OQT is one straight line, therefore OT is also a straight line. But what is exactly the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and then at point T, that is a point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of the quarter circle, that is equals to 16 units in its length, according to what is given as the question. So I write it down. OT, the straight line OT, equals to 16 units in its length because it is the radius of the quarter circle. What is the definition of line 7 QT? Line 7 QT starts from point Q, that is the center of this small circle, and then to point T, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. R is the radius that we are looking for in this question. We know that OQT is one straight line, and because of the fact that OQT is one straight line according to rule 9, we get that OQ equals to OT minus QT. Again, OQ equals to OT minus QT. So I write it down. OQ equals to OT minus QT. So OQ equals to OT, that is 16. It is the radius of the quarter circle, that is equal to 16 units in its length. Minus QT, that is R. So in total, if we found out that the length of line 7 OQ is 16 minus R. Here, the length of this line 7 OQ is 16 minus R. In the next step, I'll copy the right blue triangle OQM in a new page, and we implement the Pythagoras theorem on this right blue triangle OQM. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse OQ equals to 16 minus 1. Side QM of the blue triangle equals to R. It is the radius that we are looking for. And we already found out that OM equals to 4 times square root of 2R. So actually, this is the right blue triangle OQM that are going from the original drawing. According to the Pythagoras theorem, this right triangle OQM, QO square equals to QM square plus MO square. Again, QO square equals to QM square plus MO square. So I write it down. QO square, that is the square of the hypotenuse, must be equal to QM square plus OM square. The hypotenuse QO equals to 16 minus R, therefore QO square equals to 16 minus R square. And it is equals to QM square. QM is R, it is the radius that we are looking for, so QM square is R square plus OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square. Here we'll open the brackets on both sides of this equation and get that 16 minus R square equals to 16 square equals 256 plus R square minus 2 times 16 is minus 32 times R is minus 32R. And it is equals to R square plus 4 times square root of 2R, 4 times square root of 2R square equals to 4 square, that is 16, times square root of 2R square is 2R, because the power cancels the root and we left only with 2R. So here we have R square on both sides of this equation, so R square gets cancelled. After we cancel R square, in this side of the equation we left only with 256 minus 32R equals, in the other side of the equation we have 16 times 2R, 16 times 2R is 32R. So conclusion, we found out that 256 minus 32R equals to 32R. Here we add 32R to this equation, and here that 256 equals to 32R plus 32R is 64R. So 256 equals to 64R. Here we divide this equation by 64 and get finally that the radius of this small circle, that is the radius that we are looking for, is equals to 256 over 64 is 4. So we found out that the radius of this small circle R equals to 4 units in its length. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in 2 different methods. Our mission, the second question, is to find out the area of this green shape. So in the drawing we have a quarter circle, AOB is a quarter circle. We know that side OB equals to 2 units in its length. We also know that line segment AD equals to line segment DO, and this is angle DCB that is equals to 90 degrees in its size. And our mission is to find out the area of this green shape. Actually, the green shape is the right triangle. Therefore, our mission is to find out the area of the right green triangle, DCB. Okay, so first of all, we know that AOB is a quarter circle. Therefore, this angle AOB must be equal to 90 degrees in its side. And side AO and side OB, both those two sides are defined as the radii of this quarter circle, and therefore they are equal to each other. But it is given us the question that the radius OB of this quarter circle equals to 2 units in length. Therefore, the radius AO must be also equal to 2 units. In addition, we know that AD equals to DO. If we define AD as X, then DO must be also equal to X because they are equal to each other. It is very easy to see from the drawing that AD plus DO equals to AO. Again, AD plus DO equals to AO. And AO is 2. But AD equals to X according to our definition, and DO equals to X, also according to our definition. So AD plus DO is X plus X, that is 2X. So 2X equals to AO. But AO is 2. So 2X equals to 2. We'll divide this equation by 2 and get that X equals to 2 over 2 is 1. So here AD is equals to X equals to 1 unit, and DO that is also equals to X equals to 1 unit in its length. In the next step, I'll copy the right triangle DOB. This is the right triangle DOB in a new page, and we implement the Pythagoras theorem in the right triangle DOB in order to find out the length of the hypotenuse DB. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle DOB that they call it from the original domain, according to the Pythagoras theorem. In this right triangle DOB, DB square equals to DO square plus OB square. So write it down. DB square, that is the square of the hypotenuse, must be equal to DO square plus OB square. DB, the hypotenuse DB is the missing side, so we leave it as it is. So DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, DB square equals to 1 plus 4, that is 5. So DB square equals to 5. We take out of this equation, and we get that dB equals to the square root of 5 units in its length. dB equals to the square root of 5 units. This is side dB, it is equals to the square root of 5 units in its length. In the next step, we'll do a construction, that is to say, we'll complete this quarter circle to a circle. So I completed the quarter circle to a circle. In the next step, we will extend the radius BO by a straight line until it touches the circle. And we define the touching point of the extended radius BO with this circle. This point is point P. The radius BO, which is absolutely a straight line. Again, the radius BO, which is absolutely a straight line. And when we extended the straight line BO by a straight line, the result is BP. When we extend the straight line by a straight line, the result must be a straight line. Therefore, BP is a straight line. Again, BP is a straight line. So here we can implement rule 3. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. And therefore, the sum of the angles on the upper side of the straight line PB at point O must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle plus the missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So we know that PB is a straight line, but PB is a straight line that touches the circle at 2 points, P and B. Therefore, PB is a chord because it touches the circle at 2 points, P and B. So PB is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we found out that PB is the diameter of the circle. So I'll write it down. PB is the diameter of the circle. Okay. In the next step, we will extend side CD by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. Where the extended side CD will touch the circle. We will assume that the extended side CD will not touch the circle at point P, but in any other point. We assume that the extended side CD will touch the circle at this point. We define the touching point of the extended side CD with this circle as point G. So according to our assumption, when we complete side CD by straight line, we get peripheral angle BCG. And we know that peripheral angle BCG equals to 90 degrees because this angle equals to 90 degrees. So we have peripheral angle BCG that is equals to 90 degrees in its size, and still it doesn't subtend on the diameter of the circle. Why? Because BG is not the diameter of the circle. BG is definitely not the diameter of the circle. Why? Because from point B, you can have only one diameter. From point B, we have already created the diameter BP, and therefore BG cannot be the diameter of the circle. Therefore, we have contradiction to rule 5, because we have peripheral angle BCG that is equal to 90 degrees in its size, and still it doesn't subtend on the diameter BP because it subtends on BG that is not the diameter of the circle. Therefore, we have contradiction to rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle and we have, this is peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size, and it is subtended on MN, that is the diameter of the circle. So any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle, according to rule 5. But here we have peripheral angle BCG that is equal to 90 degrees in size, and it is subtended on BG, that is not the diameter of the circle. So we have contradiction to rule 5. And in order to solve the contradiction to rule 5, we conclude that the extended side CD will not touch the circle at point G, but at point P. And then we know we not have any contradiction to rule 5. Here, the extended side CD will touch the circle at point P. Now we have peripheral angle BCP that is equal to 90 degrees in its size, and it is subtended on BP, that is the diameter of the circle, exactly according to rule 5. Okay, again we have peripheral angle BCP that is equal to 90 degrees in its size, and it is subtended on BP, that is the diameter of the circle. Okay. What is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and ends at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this circle, that is equal to 2 units. OP equals to 2. So here the right triangle PDO, side PO equals to 2, side DO equals to 1. We've already found out that in the right triangle DOB, side DB equals to 2, side DO equals to 1, and the hypotenuse equals to the square root of 5 units. Therefore, the hypotenuse P must be also equal to the square root of 5 units in itself, because those two right triangles are identical. So the hypotenuse dP must be equal to the square root of 5 units in its length. In the next step, we will extend the radius AO by a straight line until it touches the circle. And we will define the touching point of the extended radius AO with this with the circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and that's at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, that is equal to 2 units. So here we can implement rule 11 and repeat quickly on rule 11. According to rule 11, if chord AB intersects with chord CD at point O, then the following equation will be true. Here we have chord AB intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, we can actually implement all 11 in our drawing. One put in our drawing, we have code AQ. This is code AQ that intersects with code CP. This is code CP at point D. And again, code AQ intersects with code CP at point D. So I write it down. Code AQ intersects with code CP at point D. Repeat again. Now original drawing, code AQ intersects with code CP at point D. Therefore, according to rule 11, we get that AD times DQ equals to CD times DP. Repeat again, according to rule 11, AD times DQ equals to CD times DP. AD times DQ equals to CD times DP according to rule 11. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. Again, DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. DP equals to the square root of 5 units in its length. So we found out that according to rule 11, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divide this equation by square root of 5. And finally we get that CD equals to 3 over square root of 5. So the missing side CD equals to 3 over square root of 5 units in its length. In the next step, I'll copy the right green triangle DCB in the new page and we'll implement the Pythagoras theorem on this green right triangle DCB in order to find out the missing side CB. Repeat again that our mission is to find out the error of this green right triangle DCB. Here by PT is the version for Pythagoras theorem. So actually, this is the right green triangle DCB that according to the original drawing. According to the Pythagoras theorem, in this triangle, the right triangle DCB, dB square equals to DC square plus CB square. Again, dB square equals to DC square plus CB square. So write it down, dB square, that is the square of the hypotenuse, equals to DC square plus CB square. The hypotenuse dB is equal to 5, therefore dB square is equal to 5 squared, that is 5. And it is equals to DC square. DC is 3 over square root of 5, therefore DC square is 3 over square root of 5 square plus CB square. CB is the missing side, so we leave it as it is. So 5 equals to 3 over square root of 5 square. 3 over square root of 5 square is 3 square, that is 9 over square root of 5 square, that is 5. So in total, 3 over square root of 5 square equals to 9/5 plus CB square. So here we subtract 9/5 from this equation and get that 5 minus 9/5 equals to CB square. So here we multiply 5 by 5 and then we divide it by 5 in order to overcome factor with minus 9 over 5. 5 times 5 is 25, so in total in the numerator of this expression we have 25 minus 9 divided by 5, and it is equals to CB square. 25 minus 5 is 16, so in total this expression equals to 16 over 5, and it is equal to CB square. So 16/5 equals to CB square. We take a root out of this equation and get that CB, the missing sign CB, equals to the square root of 16, that is 4, over square root of 5. So we found out that the missing sign CB equals to 4 over square root of 5 units in its length. This is the missing side CB, that is equals to 4 over square root of 5 units in its length. Repeat again, our mission is to find out the area of this green shape. It's actually the area of the right triangle DCB. So the area of the green shape is the area of the green right triangle DCB. And you know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So we choose the base of this green right triangle DCB is DC. Therefore the height must be CB, because CB creates 90 degrees with the height. This again equals 90 degrees. So the height is CB over 2. So the area of the green shape equals to the area of the right green triangle DCB. That is the base times the height over 2. That is the area of any triangle. The base is DC, the height is CB divided by 2. DC equals to 3 over square root of 5 units times CB. CB equals to 4 over square root of 5 units divided by 2. So actually found out that the area of the green shape equals to the value of this expression. So here, what is the value of this expression? We have here 3 times 4, that is 12. Square root of 5 times square root of 5 is 5 over 2. 12 over 5 over 2 is 12 over 5 times 2. So it is 12, and 5 times 2 is 10. Here we divide both the numerator and the denominator of this number by 2 and get that 12 over 2 is 6, and 10 over 2 is 5. So in conclusion, we actually found out that the area of this green shape equals to either 6/5 square units, in terms of numbers, is equals to 1.2 square units. Repeat again. The area of this green shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. So, again, we know that AOB is a quarter circle, therefore angle AOB equals to 90 degrees in its side. AO and BO, they are both the other of the quarter circle is equal to 2, therefore AO equals to 2. We already found out that AD equals to 1, and DO also equals to 1 in the first method. If we implement the Pythagoras theorem on this right angle DOB, we get that the hypotenuse DB equals to the square root of 5 units. We'll not repeat on the steps that we already done in the first method. So in the next step, we will complete this quarter circle to a circle. We have completed the quarter circle to a circle. Again, we extend the radius BO by a straight line until it touches the circle. We define the touching point. We define the touching point of the extended radius BO with this circle, this point, as point P. Again, according to, we know that BP is the straight line, therefore this angle must be equal to 90 degrees in its size, according to rule 3. We already found out in the first method that BP is the diameter of the circle, because BP is a chord that passes from point O, that is the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. So BP is the diameter of the circle. PO is the radius of the circle, is equal to 2. We'll extend side CD by a straight line until it touches the circle. We have already proved in the first method that the extended side CD must touch the circle at point P and not in any other point. Otherwise, we will have contradiction to rule 5. In order to avoid contradiction to rule 5, the extended side CD must touch the circle at point P. So here we have the right angle PDO with sides 2, 1, and therefore the missing side must be equal to the square root of 5 units. We'll focus on the white right triangle DOP, and we define angle DPO as theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle, the first missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the big right triangle PCB. In the big right triangle PCB, this angle equals to theta. This angle equals to 90 degrees according to what is given in the question, therefore the missing third angle must be equal to 90 degrees minus theta. In the next step, we will prove that the right small triangle DOP is similar to the right big triangle PCB. So write it down. We prove that the big triangle PCB, the big right triangle PCB, is similar to the right small white triangle PDO. So why the big right triangle PCB is similar to this small triangle PDO? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle BCP, the big right triangle PCB, and it is equal to this angle. That's actually POD, the small right triangle PDO. Repeat again. Angle BCP, the big right triangle PCB, equals to angle POD in the small right triangle PDO. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big triangle PCB, it will be defined as angle BPC. And it is equal to itself. So if we relate to angle theta as it belongs to the small right triangle DPO, it will be defined as angle DPO. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. So angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle PBC in the big right angle PCB, and it is equal to this angle, that is actually angle PDO, in the right small triangle PDO, put again, angle PBC in the big right triangle PCB equals to angle PDO in the right small triangle PDO. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we should prove that all the three angles in the right big triangle PCB are correspondingly equal to all the three angles in the small right triangle PDO. Therefore, the big triangle PCB is similar to the small triangle PDO according to angle similarity rule. So I write it down. So the big triangle PCB is similar. This is the sign of similar to the small right triangle PDO according to angle similarity rule. And from the fact that the big right triangle PCB is similar to the small right triangle PDO, we derive that the following relationship exists between their sides. We derive that side PD in the small triangle over side PB in the big triangle. Repeat again. Side PC in the small triangle over side PB in the big triangle equals to side DO in the small triangle over side CB in the big triangle and it is also equals to side PO in the small triangle over side CP in the big triangle. Okay, again, I shall find out that PC over PB equals to DO over CB equals to PO over CD. Again, it is actually PD over PB equals to DO over CB equals to PO over CD. PD is equal to 5 over PB. PB is the diameter of the circle, that is equal to 2 plus 2, that is 4. So PB is 4 and this equals to DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is equals to PO is 2 over CD. CD is the missing side, so we leave it as it is. So we found out that according to equation 1, square root of 5 over 4 equals to 1 over CB equals to 2 over CD. So those two expressions are equal to each other, so we get equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation 1 and get that according to this equation 1, square root of 5 times CB equals to 4. Here we divide this equation 1 by square root of 5. And finally we get that according to equation 1, the missing side CB is equals to 4 over square root of 5 units. So this is the missing side CB, and it is equals to 4 over square root of 5 units in its length. We continue to focus on the long equation 1. Those two expressions in the red color, they are equal to each other. Therefore, we get equation 2 from those two expressions that are equal to each other. So, according to equation 2, we will get that the square root of 5 over 4 equals to 2 over CD. And again, after we found out that according to equation 2, square root of 5 over 4 equals to 2 over CD. Here we cross multiply this equation 2 and get that according to this equation 2, square root of 5 here, actually here, we found out that square root of 5 over 4 equals to 2 over CD. So here square root of 5 times CD. So here actually we have the because of the fact that the big right triangle PCB is similar to the small right triangle EOB, we derived that the following relationship exists between their sides. Repeat again, the big right triangle PCB is similar to the small right triangle PDO. Therefore, the following relationship exists between their sides. That side PD in the small triangle over side PB in the big triangle equals to side DO in the small triangle or side CB in the big triangle, and it is also equals to side PO in the small triangle over side PC in the big triangle. Okay, this side PO in the small triangle over side PC in the big triangle. So it is not CD but PC. Okay, so it is PC over PC. And those two expressions are equal to each other. That is to say, square root of 5 over 4 equals to 2 over PC. 2 over PC. Here we cross multiply this equation 2 and get that according to equation 2, square root of 5 times PC equals to 2 times 4, that is 8. So according to equation 2, square root of 5 times PC equals to 8. But what is the value of PC? For the moment it's very easy to see that PC equals to CD plus square root of 5. Again, PC equals to CD plus square root of 5. So here according to equation 2, square root of 5 times PC equals to 8, so PC equals to the square root of 5 plus CD equal to 8. So in conclusion, we found out that square root of 5 times square root of 5 plus CD equals to 8. We'll open the bracket on this side of this equation, equation 2. When you get that according to this equation, equation 2, square root of 5 times square root of 5 is 5. And really square root of 5 times CD, this is square root of 5 times CD, is equal to 8. Here we subtract 5 from this equation, equation 2, and get that according to equation 2, square root of 5 times CD equals to 8 minus 5 is 3. So square root of 5 times CD equals to 3. We divide this equation 2 by square root of 5. When you get that according to this equation 2, CD equals to 3 over square root of 5. So actually, let me see inside CD equals to 3 over square root of 5 units in its length. Our mission is to find out the area of the green shape. So the area of the green shape is the area of the green right triangle DCB. And the area of any triangle equals to the base of the triangle times the height to the base over 2. Again, we'll choose the base as CD, side CD, and the height as side CB divided by 2. So the area of the green shape equals to the base that is CD times the height to the base that is CB over 2. So the area of the green shape equals to CD is 3 over square root of 5 times CB. CB is 4 over square root of 5 divided by 2. So the area of the green shape equals to the value of this expression. The value of this expression equals to 3 times 4 is 12 over square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2, so it is 12, and 5 times 2 is 10, so it is 12 over 10 square units. We divide both the numerator and the denominator of this number by 6, by 2, and get that 12 over 2 is 6, and 10 over 2 is 5. So in conclusion, we found out that the area of the green shape equals to either 6/5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay, so we finish with the second method. So in both methods, we actually found out that the area of this green shape equals to either 1.2 square units or 6/5 square units. So in the next step, we'll summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the radius of this small circle. So in the drawing, we have a quarter circle. AOB is a quarter circle. Inside this quarter circle, we have this semicircle and also this small circle. I repeat again that our mission is to find out the radius of this small circle, or the value of R. Okay, so we know that AOB is a quarter circle, therefore angle AOB, this angle equals to 90 degrees in its side. In addition, sides AO and OB, they are both the radii of the quarter circle, and therefore they are equal to each other. but it is given us the equation that the radius OB of the quarter circle equals to 16. Therefore, the radius AO must be also equal to 16. Okay, AO equals to 16. But the radius AO of the quarter circle, it is also the diameter of the semicircle. So we know that the diameter of the semicircle AO is 16. Therefore, the radius must be equal to half of it. 16 over 2 is 8. So the radius AP of the semicircle is 8, and the radius PO of the semicircle is also 8. Okay. Here we implemented all 1. We have the radius QM that is drawn to point M, that is the point of tendency obtained OB with this small circle. And whenever your radius is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction, that is to say, from point Q, we draw perpendicular on AO. Again, from point Q, we draw perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. So by doing this construction, we created quadrilateral QHOM. Inside quadrilateral QHOM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral QHOM, we have 4 right angles, and therefore we know that according to rule 6, any quadrilateral that has 4 right angles, must be this right angle flat square. So we relate to this quadrilateral QHOM as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle QHOM, side QM must be equal to the opposite side HO. But QM is R, therefore HO must be also equal to R. What is the length of PH? PH equals to PO minus HO. Again, PH equals to PO minus HO. PH equals to PO, that is 8. It is the radius of the semicircle, that is 8. Minus HO, we just write down found out that HO equals to R. So in total, PH equals to 8 minus R. So here we have external length between the semicircle and this small circle, that is to say, they are touching each other externally at point S. And whenever you have an external length between 2 circles, you can implement rule 10. According to rule 10, if 2 circles touch each other externally, then the straight line that connects their centers together passes for their touching point. The semicircle have an external length with the circle at point S, and the small circle at point S. And according to rule 10, we have the center of this semicircle is at point P. The center of this small circle is at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass to point S, that is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line according to rule 10. And therefore, actually, if PSQ is a straight line, it means that PQ is a straight line. But what is exactly the definition of line 7PS? Line 7PS starts from point P, that is the center of the semicircle, and at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8. What is the definition of line 7QS? line segment QS starts from point Q, that is the center of the small circle, and that's at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore QS equals to R, that is the radius of the small circle. And because of the fact that PSQ is one straight line, it means that PQ equals to PS plus SQ. Again, PQ equals to PS plus SQ. So PQ equals to PS plus SQ, PQ equals to PS, that is 8 plus SQ. So in total PQ equals to 8 plus R. Okay. So in the next step, I copied the right green triangle PHQ in a new page and implemented the Pythagoras theorem on this right green triangle PHQ. This is the right triangle PHQ that I copied from the original drawing. According to the Pythagoras theorem, PQ square equals to PS square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it is equals to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation and found out actually that 8 plus R square equals to 8 square, that is 64, plus R square plus 2 times 8, that is 16, times R, so it is 16R. On the other side of the equation we have 8 minus R square. 8 minus R square equals to 8 square, it is 64, plus R square, minus 2 times 8, that is minus 16, times R, so it is minus 16R, plus HQ square. Here we have 64 on both sides of the equation, so 64 will get cancelled, and we also R square on both sides of the equation, so R square will get cancelled. After cancelling those two expressions, in this side of the equation we left only with 16R, on the other side of the equation we have 16R plus HQ square. So we found out actually that 16R equals to 116R plus HQ square. Here we added 16R to this equation. We finally found out that 16R plus 16R is 32R. So 32R equals to HQ square. Here we substitute 32 by 16 times 2. So in total this expression equals to 16 times 2R, and it is equals to HQ square. Here we took out of this equation and finally found out that HQ equals to the square root of 16, that is 4, and inside the root we have only with 2R. So we finally found out that HQ equals to 4 times square root of 2R. So this is side HQ is equal to 4 times square root of 2R. But we already found out that quadrilateral HQMO is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side MO. But HQ is 4 times square root of 2R, therefore MO must be also equal to 4 times square root of 2R. So here in the drawing we have an internal notch between the quarter circle and this small circle. That is to say they are touching each other internally at point T. Therefore, we can implement here rule 9. Repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles, they touch each other internally at point P. The center of the big circle is at point O. The center of the small circle is at point M, and the straight line that connects their centers together is of course the straight line OM. So the straight line OM must pass through point P, that is their touching point. OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Because in our drawing, the big quarter circle touch the small semicircle internally at point T. Therefore, we can implement here rule 9. According to rule 9, we know that the center of the big quarter circle is at point O. The center of the small circle is at point Q. And the straight line that connects the centers together is of course the straight line OQ. And according to rule 9, the straight line OQ must pass from point T, that is their touching point. OQT is one straight line. Again, OQT is one straight line. if OQT is one straight line, it means that OT is a straight line. But what is exactly the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and that's at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of the quarter circle, that's equal to 16. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and ends at point T, that is a point of the small circle itself. So QT is the radius of the small circle, that is equal to R. R is the radius that you are looking for. So in total, because of the fact that OQT is one straight line, it means that OQ equals to OT minus QT. Again, OQ equals to OT minus QT. Here OQ equals to OT minus QT. So OQ equals to OT, that is 16, minus QT, that is R. So the total we found out that OQ equals to 16 minus R. In the next step, I copied the right blue triangle OQM in the new page, and we implemented the Pythagoras theorem on this right blue triangle OQM. Actually, this is the right blue triangle OQM that I copied from the original domain. According to the Pythagoras theorem, the right triangle OQM, OQ square equals to QM square plus MO square. OQ is 16 minus R, therefore OQ square is 16 minus R square, and it is equals to QM square. QM is R, therefore QM square is R square, plus OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square. Here we open the brackets on both sides of this equation, and finally found out that 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16, that is minus 32 times R. And it is equal to R square, and here we have 4 times square root of 2 R square equals to 4 squared, that is 16, and square root of 2 R square is 2R. Because the power cancels the root, and we have to leave 2R. Here we have R square on both sides of the equation, so R square will cancel, and after I cancelled R square, in this side of the equation we left with 256 minus 32, in the other side of the equation we have only 16 times 2R, that is 32R. So we found out that 256 minus 32R equals to 32R. Here we added 32R to this equation, and we get that according to this equation, 256 equals to 32R plus 32R is 64R. So we actually found out that 256 equals to 64R. Here we divided this equation by 64, and finally found out that R equals to 256 over 64 is 4. So the radius of this small circle R equals to 4 units in its length. We finish with the first question. In the next step, I presented to you the second question, and we solved the second question in 2 different methods. Our mission in the question is to find out the area of this green shape. Actually, the green shape, it is a right triangle, because this angle corresponds to green. So our mission actually is to find out the area of the right green triangle DCB. Okay, so in the drawing we have a quarter circle. AOB is a quarter circle. We know that AD equals to DO and OB equals to 2. Again, this angle DCB equals to 90 degrees in its size. I repeat again that our mission is to find out the area of the green right triangle DCB. So first of all, we know that AOB is a quarter circle, therefore angle AOB, this angle was 90 degrees. In addition, we know that sides AO and OB, they are both the radii of the quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be also equal to 2. Here AD equals to DO, so if we define AD as x, then DO must be also equal to x. AD plus DO is x plus x, but AD plus DO is AO, and AO is 2. It means that x plus x equals to 2. X plus x is 2x, so 2x equals to 2. We divided this equation by 2 and found out that x equals to 2 over 2, that is 1. So AD is equal to x equals to 1, and DO, that is also equals to x equals to 1. Okay, So here we implemented the Pythagoras theorem on the right triangle DOB. This is the right triangle DOB that is the curvature of the original domain. According to the Pythagoras theorem, dB square equals to dO square plus OB square. dB is the missing side, so we leave it as it is. So dB square equals to dO square. dO is 1, therefore dO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 2. So in total dB square equals to 1 plus 4, that is 5. So dB square equals to 5, we took out of this equation and finally found out that dB equals to the square root of 5 units in its length. This is side dB, that is equals to the square root of 5 units in its length. In the next step we did the construction, that is to say we completed this quarter circle to a circle. And then we extended the radius BO by straight line until it touches the circle. At this point we define the touching point of the extended radius BO with this circle, this point as point P. Okay, so what is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and that's at point P, that is the point of the circle itself. So this is the definition of a radius. Therefore OP is the radius of this circle, that is equals to 2. So here we implemented all three. BO is a straight line, and when we extended the straight line BO by straight line, the result is BP. Therefore BP is also a straight line. We implemented here all three. According to all three, the sum of the angles on the upper side of the straight line BP at point O must be equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle, that is the right angle, plus the missing angle. In total they must be equal to 180 degrees, therefore the missing angle must be equal to 90 degrees in its size. Okay, so we know that BP is a straight line, but BP is a straight line that touches the circle at 2 points, B and P. Any straight line that touches the circle at 2 points is defined as a chord. So BP is a chord. BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. We extended side CD by straight line until it touches the circle. The question is where the extended side CD will touch the circle. We will assume that the extended side CD will not touch the circle at point P, but in any other point. For example, this point G. And therefore we have here peripheral angle BCG, that's equals to 90 degrees in size according to what is given as the question. And it doesn't subtend on BP, that is the diameter of the circle, but it is subtended on BG. BG is definitely not the diameter of the circle. Why? Because from point B you can draw only one diameter to the circle, and we have already drawn the diameter of BP, and therefore BP only one diameter, that is BP. Therefore BG cannot be the diameter of the circle. So we have here contradiction to rule 5, because we have peripheral angle BCG that is equal to 90 degrees in size, and still it doesn't subtend on the diameter of the circle, but it is subtended on BG, that is not the diameter of the circle. So we have contradiction to rule 5. In order to solve the contradiction to rule 5, we have to conclude that our assumption that the extended side CD will touch the circle at point G is not correct. And therefore, we must conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we have contradiction to rule 5. Now, we know that the extended side CD will touch the circle at point P. So we have here peripheral angle BCP. Peripheral angle BCP equals to 90 degrees in size, and it is subtended on BP, that is the diameter of the circle, exactly according to rule 5. So here we have the right angle DOP, side DO equals to 1, side PO equals to 2, therefore according to the Pythagoras theorem, the hypotenuse must be equal to the square root of 5 units. We've already done it here. So the hypotenuse DO equals to the square root of 5 units in its length. We extended the radius AO by side line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of this circle, and ends at point Q, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore, Q is the radius of this circle, that is equal to 2 units. So here we can implement rule 11. Repeat quickly on rule 11. According to rule 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, chord AB intersects with chord CD at point O. Therefore, according to this rule 11, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ. This is chord AQ that intersects with chord AP at point D. Whenever we have two chords that intersect with each other in the circle, we can implement rule 11. Again, we have chord AQ that intersects with chord CP at point D. Okay, again, chord AQ intersects with chord CP at point D. Therefore, according to rule 11, AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. Okay, again, according to rule 11, AD times DQ equals to CD times DP. AD is 1, DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, times DP is equal to 5. According to rule 11, we found out that 1 times 3 equals to CD times equal to 5. 1 times 3 is 3, so 3 equals to CD times equal to 5. We divided this equation by equal to 5, and finally found out that CD equals to 3 over equal to 5 units in its length. The missing side CD equals to 3 over equal to 5 units in its length. Then I copied the right green triangle DCB in a new page and implemented the Pythagoras theorem on this right green triangle DCB in order to find out the missing side CB. Okay, so actually this is the right green triangle DCB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle DCB, DB square equals to DC square plus CB square. DB is equal to 5, therefore DB square is equal to 5 square, that is 5. Plus DC square. DC is 3 over square root of 5, therefore DC square is 3 over square root of 5 square plus CB square. CB is the missing side, so we leave it as it is. So 5 equals to square root of 5 squares. 5 equals to 3 over square root of 5 square. 3 over square root of 5 square equals to 3 square, that is 9, over square root of 5 square, that is 5. So in total, this expression equals to 9/5 plus CB square. Here, subtract 9/5 from this equation, and finally found out that 5 minus 9/5 is equals to CB square. We actually multiplied 5 by 5 and then we divided it by 5 in order to have a common factor of minus 9 over 5. 5 times 5 is 25, so in total in the numerator we have 25 minus 9 over 5 equals to CB square. 25 minus 9 is 16, so in total this expression equals to 16 over 5, that is CB square. We took out of this equation and finally found out that CB equals to the square root of 16 is 4 over square root of 5. So CB equals to 4 over square root of 5 units in its length. This is side CB, it equals to 4 over square root of 5 units in its length. Our mission is to find out the area of this green shape. The green shape, it is actually the right green triangle, triangle DCB. So our mission is to find out the area of the green right triangle DCB. And the area of any triangle equals to the base of the triangle times the height to the base over 2. So the green shape is the right triangle, and the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base as CD, and the height is CB because it creates 90 degrees with the base. So again, we choose the base as CD, and the height is CB. CD equals to 3 over square root of 5, CB equals to 3 over square CD equals to 3 over square root of 5, CB equals to 4 over square root of 5 divided by 2. So the area of the green shape equals to the value of this expression. This expression equals to 3 times 4 is 12 over square root of 5 over square root of 5 times square root of 5 is 5 divided by 2. And 12 over 5 over 2 is 12 over 5 times 2. This is to say it is 12 times 5 times 2 is 10. So it is 12 over 10. We divided both the numerator and the denominator of this expression by 2. 12 over 2 is 6 and 10 over 2 is 5. So in total I found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers it is equals to 1.2 square units. We finish with the first method. In the next step I presented to you how to find out the area of this green shape according to the second method. In the second method, actually we know that AOB is a quarter circle, therefore angle AOB equals to 90 degrees. AO equals to OB, they are both the radii of the circle that is equal to 2, therefore they are equal to each other. We already found out in the first method that AD equals to 1 and DO equals to 1. And then here we can implement the Pythagorean theorem on this right triangle, and the hypotenuse is square root of 5. Then we did the construction, that is to say we completed this quarter circle to a circle, and then we extended side BO, the radius BO by straight line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. BP is the straight line, and therefore this angle equals to 90 degrees according to rule 3. And BP is the straight line that touches the circle at 2 points, B and P. Therefore BP is a chord that passes through the center of the circle, that is to say from point O. Therefore we know that any chord that passes through the center of the circle is defined as a diameter. Therefore BP is the diameter of the circle. Then we extended side CD until it touches the circle. In the first method, we proved that the extended side CD must touch the circle at point P, not in any other point. Otherwise, you will have contradiction to rule 5. Okay. So here we have the right triangle DOP. Side DO equals to 1, side OD equals to 2, therefore according to the Pythagorean theorem, the hypotenuse equals to the square root of 5 units. We focus on the right triangle DOP. We define this angle DPO as theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, focus on the big right triangle PCB. On the big right triangle PCB, this angle equals to theta. This angle equals to 90 degrees. Therefore, this missing fourth angle and this missing third angle must be equal to 90 degrees minus theta. In the next step, we proved that the right big triangle PCB is similar to this whole right triangle PDO. So why the right triangle PCB is similar to the right triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the angles of the right triangle PCB are correspondingly equal to all the angles of the right triangle PDO. Therefore, the right big triangle PCB is similar to the right small triangle PDO according to angle similarity rule. So I repeat again, found out actually that the right big triangle PCB is similar to the right small triangle PDO according to angle similarity rule. And from the fact that the two triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side PD in the small triangle over side PB in the big triangle equals to side DO in the small triangle over side CB in the big triangle, and it is equals to side PO in the small triangle over side CP in the big triangle. PO is equal to 5, PB is 2 plus 2, that is 4, DO is 1, CB is the missing side, so we leave this it is, PO is 2, and PC, what is the length of PC? PC in total equals to the square root of 5 plus DC. Again, PC equals to square root of 5 plus DC. Okay. So, I should have found out that PD is square root of 5, PB is 4, DO is 1, CB is the missing side, so we leave this it is, PO is 2, and over PC. Here, those two expressions are equal to each other, therefore we created the equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here, of course, multiply this equation and equation 1, and finally found out that square root of 5 times CB equals to 4. Here we divided this equation 1 by square root of 5, and finally found out that the missing side CB equals to 4 over square root of 5 units in length. This is the missing side CB, that is equal to 4 over square root of 5 units in length. Those two expressions in the red color, they are equal to each other, therefore I created the equation 2 from those two expressions that are equal to each other. So according to equation 2, we actually found out that square root of 5 over 4 equals to 2 over PC. Repeat again, according to equation 2, we actually found out that square root of 5 over 4 equals to 2 over PC. Okay. But what is the size of PC? PC in total equals to square root of 5 plus DC. Again, PC in total equals to square root of 5 plus DC. Okay, so here of course multiplied this equation 2, and found out actually that square root of 5 times PC equals to 4 times 2, that is 8. So square root of 5 times PC. And we just write down found out that PC equals to the square root of 5 plus CD. So according to equation 2, we actually found out that square root of 5 times square root of 5 plus CD equals to 8. We opened the brackets of this equation 2 on this side of the equation 2, and found out that square root of 5 times square root of 5 is 5, and square root of 5 times CD equals to the square root of 5 times CD. That's equal to 8. Here we subtracted 5 from this equation 2, and finally found out that according to this equation 2, square root of 5 times CD equals to 8 minus 5 is 3. So square root of 5 times CD equals to 3. We divided this equation 2 by square root of 5, and finally found out that the missing side CD equals to 3 over square root of 5 units in its length. This is the missing side CD, that is equals to 3 over square root of 5 units in its length. Our mission is to find out the area of this green shape. The green shape it is actually the right green triangle DCB. Okay, and the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base as CD and the height as CB, because the height CB can 90 degrees with the base. Again, the base is CD and the height is CB over 2. CD is 3 over square root of 5 times CB. CB is 4 over square root of 5 over 2. So they have the green shape equals to the value of this expression. The value of this expression equals to 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So it is equals to 12 over 5 over 2. 12 over 5 over 2 is 12 times 5 times 12 over 5 times 2. So it is 12 and 5 times 2 is 10, so it is 12 over 10. We divided both the numerator and the denominator of this number by 2, and found out the 12 over 2 is 6, and 10 over 2 is 5. So if we found out the area of this ring shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. So in both methods, we arrive to the same results. The area of this ring shape equals to either 1.2 square units, or in terms of numbers, it is equals to 6/5 square units. Okay, thank you very much.